Okay, so what does K really tell us in an equilibrium problem? K is different. The big K is different than the little k that we dealt with in the kinetics unit. And the magnitude of K really tells us whether we have a forward reaction favored or a backward reaction favored. And so if we look at K is greater than 1, that means that the reaction really wants to create products because mathematically the numerator would be greater than the denominator here. So it really makes sense that if K is greater than 1, meaning our products are higher and our reactants are lower, and that's where the reaction is going, then the forward reaction is favored. It is product favored is another way that we can talk about this. If K is really, really big, 10 to the 30th, 10 to the 40th, what we can say is that the reaction goes to completion, meaning it is so forward favored that there's really very little, if any, reverse reaction that happens. Examples of things that this happens to are things like combustion. We can't reverse a combustion reaction, or we don't reverse combustion reactions. Strong acid dissociation. So when an acid breaks apart in solution, it will break into H plus and Cl minus, or Br minus or whatever, and that doesn't reverse back. Now, if we have a situation where K is less than 1, that mathematically makes sense that then reactants are greater and products are less, which means that it stays in reactants more than it wants to make products. And that means that the reverse reaction is favored, or it's reactant favored. Now, if K is really small, like 10 to the negative 30th, the reaction really does not occur to any significant extent. That means that there's a lot of reactants still in solution, and there is very, very little products or whatever. So this is an example here, and this one, like I said, has 10 to the negative 30th. So like I said, that's a time where the reaction really doesn't go in the forward direction, and it sits really far on the reactant side. Now, if we look at this, it's important to realize that the size of K and the time required to reach equilibrium are not directly related. Here's the key. Big K means that the reaction is going to go in a forward direction, that the product is product favored. Little k that we talk about in kinetics is not the same thing. And a big K does not mean it's going to happen. A big K, a big capital K, does not mean that it's going to happen quickly. Okay, it doesn't say anything about the time it takes to get the reaction to go in the forward direction. So a large K does not necessarily mean, oops, I need to get my pen. A large K does not necessarily mean that the reaction will reach equilibrium quickly. It just means that it will go in the forward direction. Now, predicting the direction of a reaction. For a reaction that is not at equilibrium yet, what we can do is we can calculate the ratio of products to reactants. It is a snapshot of what the conditions are at that moment. It would not be K, it would be called Q. We calculate it the exact same way. So it's calculated the exact same way, concentration of products over concentration of reactants. But instead of being K, it's Q, because we don't know, it's not at equilibrium at that point. It is a very valuable piece of information because it'll let you know which direction the reaction has to go to get to equilibrium. So go ahead and try to take a moment and do this example right here. Pause for me, and then as soon as you have calculated it, press play, and then you can see what the correct answer is once we get to the next. So now, hopefully, you got this where you did concentration of products over concentration of reactants, again, following stoichiometry. So you should have gotten 2.8 times 10 to the 7th. Now, it asks, which direction will the system proceed to reach equilibrium? So let's talk about which direction what would happen here. It makes sense mathematically, but I want to talk it through really quickly. So if your Q is greater than K, so remember, K is what it is, what the concentration should be at equilibrium, what the ratio of products to reactants should be at equilibrium. If Q is greater than K, then the ratio of products to reactants is too high. And we need to convert products back to reactants. And remember, it's products over reactants equals K. And if our Q is too big, that means we have too many products, okay? And we need to shift it back to the left in order to get more reactants and get to our K. So the system will shift to the left to reach equilibrium. Oh man, left. Okay, now if we solve for Q here, if we solve for this right here, and our Q is equal to K, then guess what? The system is at equilibrium. Yay. And it won't shift either way because at that point it is at equilibrium and it's sitting right there. Now, if Q is less than K, then the ratio of products to reactants is too low. And we need to convert some of the reactants back to products. The system will shift to the right to reach equilibrium. Now, let's go back to our problem here. We know that the K in a certain experiment, the K for the reaction should be 6.5 times 10 to the fourth. That's what it says our K is. Now, in this case, our K is not that, or our Q is not that. It is 2.8 times 10 to the seventh. And in this case, we know that our Q, this guy that we have right here, is actually greater than our K. So our Q is greater than K. Going back to our table, if Q is greater than K, we have too many products, not enough reactants. It is going to shift this reaction back to the left. So you should have gotten that this is going to shift to the left to make more reactants.